the last part of the course. I wanted to do some more on optics today because, again, some of you have been taking a lab, and I wanted to prepare you a little bit better, if I can, for that. So I changed my notes on the ray optics because I wanted to show you a couple of demos that were not in that original PowerPoint setup. I'll send you a revised version tomorrow. There's yet some more revisions I want to make, namely to add something about the vision of how the eye works. I think that's very important that you understand. Yeah, that's a good subject. Fascinating, actually. So, but I wanted to go back over some things here. We'll view this. Where are we? No, I want to go back to here. Yes. Okay. So we didn't do this very thoroughly, but I think some of the things are very interesting and simple, namely the incident reflected ray and the law of reflection, which says that if you judge things from the normal to a surface, the angle between the incident beam and the outgoing beam with respect to the normal are equal in the case of reflection. That's pretty obvious. Bounces this way, bounces out that way. What's more complicated is when the light travels into the material, comes in. The easy part is it bounces off at the same angle. Theta 1 prime is equal to theta 1. What's more complicated is the fact that it bends toward the normal if it goes into a more dense material, and it's given by Snell's law. Quickly going over this one more time. What stays constant when that light, any electromagnetic radiation, enters a new denser medium and slows down, the factor that changes when the speed changes is the wavelength. In other words, the fellows who go into the slower medium, they go at the same timing, but the fellows going faster catch up with them, and so their wavelength gets smaller. So you just should know that. And we said that there are varieties of the slowing down of the speed depending on the material. Typically for solids, most solids, it's about 1.5 in the visible range. But it can vary, and we'll get into that, I keep saying, as we go into more depth on just what's going on here. Then we had an explanation of Snell's law, which depended on the fact that although we're talking about rays, and here the rays is the direction that between, say, perpendicular to the crests, which someone asked, what is these wave crests or wave fronts is another word that's used here. The ray is perpendicular to that. It's the direction in which the wave is traveling rather than the direction along the crests. Okay? And we can derive that on wave properties. Now, then we had the idea of total internal reflection. And I also talked about polarization by reflection. Now, we had a little office hour before this, and I could see that, and it's reasonable to be a little bit mixed between those two things because there are a lot of things that are similar and yet they're different. So let me just quickly sort out what we're talking about here because there's a lot of similarities, but they are different. One is, which one came first? The critical angle, which is sometimes called TIR, total internal reflection. And the words mean very well said. It's total, meaning it's complete. Internal, meaning that if I have a solid material, internal to that, the light is totally reflected. So the words say exactly what it is, which means that normally you would expect that when light meets a boundary, some of it is reflected, sure, but some of it should refract and go out into the second medium. In this case, let's call this medium 1 because that's the from which it's coming, and this let's call medium 2. What it turns out is that at a certain critical angle, is this in the way for some of you? At a certain critical angle, the angle of refraction is 90 degrees. So there's where a 90-degree story enters, there, between the normal and the refracted beam. So let me maybe show that. See, the refracted beam would go 90 degrees. If the angle gets any greater than that, this thing wants to bend more than 90 degrees, which means bend more than 90 degrees, which means it stays inside the material. So from here on out, the light cannot get out. See, when light comes straight along the normal, it gets out perfectly fine. Some gets reflected, actually, of course, but it can get out. But when it's beyond the critical angle, the angle of refraction is 90 degrees. So that's one thing that has to do with refraction, and there's a 90-degree story in here. Now the confusion comes in, so this is total reflection. Then we have the other idea of the polarization angle, or Brewster angle. And here the story is a little bit different. Here we're talking about a reflection at a surface. The light comes in, and the light refracts, and the light reflects. This should have been the same angle. Let me revise this one to make the angle of reflection equal, best I can draw it. So theta in, theta reflected here, equal, right? Okay, so that part is good. Now there's another 90 degrees in here, but that's this 90 degree. There's a 90-degree angle here. So these are two different stories. The idea here is that you come in with unpolarized light. And somebody in the office had this very good image, namely of the bristle brush, the bottle brush with all the bristles sticking out in every direction. That's what comes in this way. It's got all the polarization directions. In principle, they all come in. When you come out here, it's taken a haircut. Oh, there's another image of these guys that have their haircut like this with a tomahawk. What do they call it? Tomahawk? What is it called? Mohawk. Yeah, it should be tomahawk. It's a mohawk, and it's been mohawked in this direction. Yeah, that's what happened. The bristle brush has been mohawked, and you end up with one direction. The reason is because of this 90-degree angle here, the wave is vibrating the medium, and the vibrations that are vibrating this way, because this direction of reflection is at 90 degrees, it's along the axis of these vibrators, the material, and this does not radiate in that direction. It only radiates in this direction. These guys radiate in this direction, and so you end up with polarization like that. So you want to be clear on these 2 points. It's a different phenomenon. This gives you a polarization. There is a 90-degree story in here. There's a 90-degree story in here. It's a different story. And the other thing we could run through is that they both are susceptible to Snell's law, which governs refraction, which is, okay, let me write Snell's law once for all up here. N1 is the medium you start with. N1 sine theta 1 equals N2 sine theta 2. So all you do is you apply that law, but interesting things happen because of this 90-degree angle, and you're going to have a sine of theta, and a sine of 90 is 1, And you're going to build in another story when you have this angle being 90 degrees. So for example, in this case here, we're saying, what angle would I have to come in with to make this refracted angle 90 degrees? That's the question. So I would write Snell's law as I come in from medium 1, N1, let me start a little higher, N1 sine theta 1 equals N2 sine theta 2. But theta 2 is 90 degrees. Isn't that nice? Theta 2 is 90 degrees, so sine of theta 2 is 1. So I just put in Snell's law, sine theta 2 is 1, so I get N1 sine theta 1 equals N2. And so that's at this critical angle in particular. So I have sine theta of the critical angle is equal to N2 over N1. Now sines must be less than 1, so it says that N2 must be less than N1. So you can only get this when N2 is less dense than N1, because then the light coming to the surface bends away, and what you're trying to do is get it to bend 90 degrees to the normal. So it can only happen when you're going from a dense to a less dense medium. That's all. It's just very simple. And this is the thing you'll find in the book. All you're doing is taking advantage of the fact that at the critical angle, the refracted beam is now parallel to the surface, and beyond that, it doesn't get out. So here we do a similar thing, taking advantage of this 90 degree in this story. So we do Snell's law again. N1 sine theta 1 equals N2, let me abbreviate, sine theta 2. Okay, so here our first medium, say, is this one, and our second medium is this one. So, okay, I have sine theta at the Brewster angle. You'll have N2 sine of theta 2. Now we use the idea that this angle must be 90 degrees at this point. So we want to build this. See, I want to try to get what is theta, the incident angle. I'd rather not have it involve theta 2. I really want to know what angle should I send the light in order to get it polarized coming out. So I'm really trying to get everything to have only theta incident in my formula. So I'm trying to get rid of theta 2. But I can't get rid of it because I know that this is theta 1, this is 90, this is theta 2. So the sum of these three is 180 degrees. So I can write that theta 1 plus 90 plus theta 2 is 180. Isn't that nice? All right, so I take off 90 from here, I get 90. So I'm trying to get everything in terms of theta 1. So I can say theta 2 is 90 minus theta 1. Right? And you can recognize that. Okay, let me draw a little triangle here. If I have theta 1, this is a right triangle with angle theta 1. 90 minus theta 1 is this, right? Because this is 90. So, and the whole sum is 180. So this one is theta 1, or 90 minus theta 1, right? Which is, okay, so and if I want to take the sine of theta 2, the sine of 90, the sine of that is this over the hypotenuse. That's the sine of 90 minus theta 1, but that's also the cosine of theta 1. So the sine of this old trigonometry that we dearly love, sine of 90 minus theta 1 is the cosine of theta 1. That's sort of the cosine of the complement, you remember these vega rules, which you can just derive it. So what we get here, finally, let me write it over here, is that we have N2 sine, okay, let me do N1, sine of theta of the Brewster angle is equal to N2 cosine. It was the sine of 90 minus the Brewster angle, so it's now the cosine of theta Brewster. So the Brewster angle occurs when you have sine, now I'm going to bring all the Brewster angle things on one side, cosine theta Brewster, and I get N2 over N1. And the sine over the cosine, we remember from trig, is tangent of theta b. So that's the formula for the Brewster angle. And we've just nicely used the fact that those two rays are at 90 degrees from each other because of the mechanism of radiation by these dipoles driven in the material. Now it's interesting that the Brewster angle, can you get polarization when N2 and N1 are greater, when this is greater or less than 1? In other words, you can get it off when this medium is more dense or less dense and more dense. In other words, would you get it coming this way too? Could you? And the answer is yes. There's no real reason because the tangent doesn't have any limit. The tangent can be as much as infinity. So you could get polarization when you go, if you have a medium from light air to a solid, you can get polarization at some angle. Interesting. And on the other hand, you could also get it when you're going this way inside the medium, but it'll be at a different angle. In other words, it's interesting. I don't know which angle is bigger. We can easily figure out which. When N2 is larger, when it's bigger than 1, it's more than 45 degrees. And when N2 is less than N1, tangent of theta is less than 1, so it's less than 45 degrees. But it could happen either way, which is sort of unlike this phenomenon here. I just pass that on to you, so don't get them confused. They're two different phenomena. There is a 90-degree thinking in one and a 90-degree thinking in the other, but they're doing, well, it's a little, and deep down, it's the same phenomenon. It's how the dipoles are vibrating. But here it's glaring that the dipoles simply don't radiate the polarization in this direction. So you're only left with that polarization. Okay, so I hope that helps a little bit. Yes, ma'am? It's totally the same. Well, oh, actually, in some sense it's the same. We're using the word polarization in some different sense. I don't know which senses you're using it, asking about. But we do have the idea that if you put an electric field on a material, you polarize it. That's one polarization. Here we're talking about something different. Here I have an electromagnetic wave, which is composed of electric and magnetic fields. And I'm choosing the direction of the electric field, and I'm calling that the polarization direction of this electromagnetic field. So they are different. We use polarization an awful lot, I'm sorry to say. Yes? Yes. That's right. That's right. Then we're talking about the polarization of light, and we're talking about the fact that the light has, the E fields have a particular plane of vibration, and if the polarizer is aligned, has its polarization direction in line with that light, that's we call that polarization direction of the polarizer. That's the direction of radiation vibration that passes through. Does that answer your question? This thing here. Yes. Why does it change? Why does it polarize the light? That's a very good point, and I try to explain it in the following way. The thing comes in unpolarized, like that bristle brush with every different direction. It hits the surface. The surface reacts to that light because it's made of electrons and protons and stuff. So it starts vibrating. And those vibrations radiate. It's like an antenna. The atoms in the material are driven antennas. But the key thing about the vibration, this is a very deep question. I tried to answer it a few times, but it's hard to grasp. If you have vibration up and down an antenna, the antenna radiates to the side. It does not radiate in that direction. You have to get a component of acceleration in the direction you're trying to radiate. It does not radiate in this direction. That was something I showed when I had this long antenna. I try to go to the end of it, and it doesn't radiate this way. It's just the way dipole fields are. They go like this, and there's nothing along the axis radiated. So if I'm the material here, and a light beam comes along this way, granted the material here is being vibrated by all those polarizations. It's also a bristle brush in here. But what does it radiate? What do these guys radiate? The ones that are vibrating this way radiate in all directions sideways, like this. So they're radiating this way, the ones that are going here. So they are radiating the new reflected wave. The ones that have polarized this way, you see my thumb is pointing in that direction, it doesn't radiate in that direction, so there's no polarization like this. Get that? That's the deep reason behind the polarization effect. My thumb is, because they're vibrating this way, no radiation comes this way. So I end up, this polarization is radiated this way, so I get this polarization. This one is radiating this way, it's radiating sideways, sort of like this, but it's not radiating in that direction. A slit, just a simple slit. Yes, a slit alone won't do it. What you have to, well, a polarizing screen has a preferential direction because there are molecules in here. Well, a single slit won't do it. We did have a grill of things. Yeah, a grill. If you have enough of them, they will block the waves that are trying to get through and they're vibrating this way. They'll be creating currents up and down those grill wires and sort of use up the field. So that's why you have to turn the grill sideways. So when it vibrates, it doesn't give you as much current sideways. But so this is the passing direction because it doesn't use up the field. So that is a polarizing direction. Second. Well, yes, it's slightly different mechanism. Yeah, it's pretty much the same mechanism. When I'm doing this, these are acting as picking up antennae. So if my field is going like this, these antennae are picking up the field, and then they're reducing the field behind them because they've caught some of the waves, and some of those waves are driving the electrons up and down, using up some of the wave's energy. So the wave doesn't get through the grill if the wires are this way. These are properly aligned antennae. If you want to pick up the wave, you want your antenna this way. But it will block the wave. It uses it up because you've taken something from it. If you have enough of them, it'll stop the wave entirely. It's a very good point. I mean, it's not easy to grasp the first time through, but so it's good. Now, yes, sir. It's perpendicular to the reflected direction. Yes, that's a very, I'm trying to find that very well. But what we usually do, if you have an incident beam coming in, we do some, should have a pen. If you have an incident beam coming in and a reflected beam going out, we define this as the plane of incidence. In other words, if I have a ray coming in, it'll bounce off in the same plane. So that's a plane of incidence. Yeah, and here's my surface, right? So now I have polarizations in all directions like this coming in. And on my way out, I only have polarizations this way because the medium can't project polarizations that way. So this is what's called the plane of polarization. Got that? Yes, sir. It's partially polarized, partially, because you sucked out some of the energy from one of the polarizations. So it's partially polarized. Pardon me? Means that you won't have as many guys vibrating this, a stronger field vibrating this way as that way. It's just, that would say that the electric field, see, the strength of the field is given by the magnitude of the field. But so you'll have, in the bristle brush analogy, you'll have taller bristles in one direction than the other. So it's partially polarized. An unpolarized wave, all the bristles would have the same length around the, you see my image of the bristle brush? So they would all have the same length, they all have the same strength. On the other hand, it's partially polarized, and it might be elliptical, namely they have more strength in that direction than that. So that would be partially polarized because there's more electric field strength in that direction than in that, because some of it has been radiated out. Okay, let me move ahead because there's some little fun things, and I also wanted to get to relativity today. Oh, I don't think I'm going to make it again. But anyhow, I wanted to see these demos. So in any case, the story is that the subject is not as complicated as it might seem because we treat mirrors and lenses with the same formula. You just have to know what they mean. You have the situation, I think you've already maybe experienced it in the lab, where you put an object in front of a lens or a mirror, and then light passes